So, welcome everyone to the Good Vibrations seminar series. And today, Tiago will be the chairman.
Okay, so hello everyone. I think we should get started, right? So as Rita said, welcome to the second installment of the Good Vibes seminar series. I'm sure that most of you are now fully aware of what this is about. So this is a series of invited seminars dedicated to astroseismology and related fields, given by young astronomers. And so, if you are a PhD student and you would like to give one of these seminars, please feel encouraged to do so. The application process is very straightforward. You just go to our website and you can apply. The details for the application process are stated there. So please do so. Well, with this out of the way, let me then introduce today's speaker, Filipe Pereira. So Filipe did his master's at the University of Porto, where he developed an automated tool for measuring acoustic glitches in solar type stars. And he then embarked on a PhD, still at the University of Porto, but now doing something slightly different, detecting and characterizing planets around oscillating red giants. And I think we will hear more about that today. So before we start, let me remind you of how this works. So the talk will be about 45 minutes long. Please do not interrupt Philippe during the talk, but write down your questions in the chat. Okay, I will check them in the end and give you the word. And well, if you prefer, you can then just raise your hand at the end of the talk, and I will take your questions also. So, without any further ado, Philippe, it's on to you. The floor is yours, and good luck.
Thanks. So, hi everyone. Hopefully, everyone can hear me well. So as Tiago said, today I'm going to present the work that I've been developing in my PhD project, which is the detection and characterization of planets orbiting oscillating red giant stars with NASA's TESS mission. And I know this is the Good Vibes seminar, so it's probably very clear by the title right now that my project clearly veers a lot towards planets. And specifically, it's not just planets around red giant stars, it's specifically close-in planets, giant planets around red giant stars, meaning what is usually called hot Jupiters. Now, it is important to note that obviously there's a lot of planets here, but astroseismology is very much important to my project, the meaning, the reason why there's oscillating there in the title. And the reason is basically every planetary parameters that we derive from a stellar light curve is essentially a quantity that is dependent on the values that we have for the star. And so that means that whatever value we want to actually get with enough precision, we need to make sure that we actually get stellar values with enough precision to describe the planet well. And again, astroseismology obviously helps with that because it resolves a lot of degeneracies in the known properties of the star. It also gets very much high precision in the values in the stellar parameters. And so it's very much desired that we actually get those the astroseismology in the stars where we're looking for planets. So just to give you a small reasoning for why we would want to look at these Jupiters oscillating evolved systems. First, in the context of the dynamical evolution of planetary systems, we have the fact of theory predicts that when these systems, when these stars become evolved, it is expected that these close-in giant planets would spiral in towards the stars and eventually in this evolved state be engulfed by the stars. Now, the initial RV surveys that were looking at evolved hosts didn't find any kind of these hot Jupiter planets, and upon trying to get an occurrence rate for these planets, noticed exactly this. So they noticed the fact that because there were no planets there, the occurrence rate seemed to be lower than the one expected for main sequence stars, which was in accordance with the theory that they would eventually be engulfed. However, more recent results for K2 stars with planetary transits instead of just RV surveys observed that the occurrence rate for these evolved hosts actually seemed to be more in line with what was being observed in main sequence, which kind of raised the question of why is there this discrepancy between the RV surveys and the transits? Is it actually the theory that these evolved systems, the engulfment should be happening a bit later than what is being observed by the photometry? Is it something else in the theory that is wrong? Now, because this studies was basically done with 3 stars on the K2 photometry survey, there's all this interest of looking for more planets to actually do a study with a bit more of planets and more stars overall. And obviously TESS here helps a lot compared to K2 because we're looking at a much larger number of stars all around the sky. And so this is the motivation for looking at this scientific problem in the context of TESS. Now, the other very much interesting issue related with these hot Jupiters is the radius inflation. Now, ever since these hot Jupiters have been observed, both in evolved systems and in main sequence systems, their radii has been noticed to be larger than what would be normally expected by theory of the formation of these planets. And also, at the time it was observed that this increase in radius above the theory also happened in line with increased irradiation from the host star. Two groups of theories showed up, a lot of theories on both, but two groups showed up that tried to explain this inflation of the radii. One group explained this inflation by the reinflation of the radii. So the radius from the planet is inflated at formation. It then goes back to its normal radius, and then radiation from the host star deposits energy into the planet's core, which causes the planet's radius to reinflate and be observed higher than predicted. The other theory is the other way around. So it assumes that this irradiation from the host star is actually delaying the cooling of the core of the planet by depositing irradiation there, which means that the inflated radius from formation is actually larger, and then it just delays the cooling, and eventually it goes back to the expected theoretical radii. Now, Lopez and Fortney in 2016 observed a very interesting fact, which is if we look at evolved stars, so if you look at these hot Jupiters around evolved stars, first, these systems are a lot older, and so if there is a delayed cooling happening, there's been plenty of enough time for that to happen. And at the same time, the radii of these systems, of these stars, is larger, and so the irradiation on the planet is also larger. And so if these planets are there, if we find them, then supposedly we could be able to identify if any reinflation would have happened to them and relate it with the stellar irradiation. And initial results, again, for giant planets orbiting giant stars point to a reinflation of the star. So they point to the fact that in these evolved hosts, the radii seem to be actually larger. But again, this study was done with basically two stars, so two planets, around 2 stars. And so there's, again, very much an interest in looking at TESS to see a much larger sample of stars, to look at a lot more of these systems, increase the sample to actually redo these tests and confirm if this is actually true. And then there's also a couple of other minor, at least in the context of hot Jupiters around evolved systems, there's a lot of other minor questions. There's correlations, positive correlations between stellar mass and the occurrence rate of giant planets, both close in and farther away. Now, these initial studies on the occurrence rate to stellar mass were made with RV surveys, with spectroscopy, and there's been some discussion on the literature mainly about the masses of these, if the masses are correct or not. Just in this case, looking at stars with actual astroseismology would very much help, because we'd be able to have this mass with maybe more accuracy, which would, obviously the sample would be a lot smaller, because there's this lack of close-in giant planets, but maybe it would be it would improve this question. And again, correlations with metallicity and the occurrence rate of giant planets has been established for main sequence and subgiants, but for red giant stars, there doesn't seem to be that correlation. But I don't think it's been very much studied in the literature, and maybe again increasing the sample with TESS might help with this type of question. And now, given all of this motivation, I want to talk about the two things that I mostly did during my PhD. So the first thing was a systematic search for transits of giant planets around with short orbits. I look for lower than 20 days, but I'm mostly focused on lower than 10 days and around evolved stars observed by TESS. So this was one of the parts. The other part was to try and improve the characterization of these systems around the evolved stars, because it isn't as straightforward as the characterization of planetary systems around main sequence stars. And I did some work on that. And I'm actually going to start by the characterization, just because it's the way I followed the work in my PhD. And I think it also makes more sense in this case. And so starting with the characterization, so describing, characterizing or modeling planetary transits for main sequence stars is a lot simpler than for evolved stars. And the reason is the usual part is to deal with the star, which in the case of planets is usually considered a noise. We actually normally just filter them out for main sequence stars and then actually recover the planetary parameters. However, for evolved stars, the timescales of the granulation and the oscillations happen on the same timescales as the durations of the transits. And so for this reason, obviously, filtering out is not possible, because we might mess up with the transits, and that's not what we want to do. And also because these stars are larger, have larger radii, the amplitudes of these signals are also larger, especially compared with the transits. And so this becomes a bit more difficult. And so the idea here is not to filter it out, not to consider the star noise, but actually to model both of them together in the time domain. So to account for both the star and the transit in the light curve, and model both of them together. Now, for modeling stellar signals, I imagine people from astroseismology might be more comfortable with this vision, with this image. So we have a power spectrum, and the background power spectrum is normally the stellar signals are normally modeled in this power spectrum by the background model. So you have your granulation modules, which are modeled by Harvey-like functions. We have also a Gaussian-like function modeling the entire envelope of the oscillations, and we have like a flat line, which is modeling which would be modeling the white noise. Now, unfortunately, we can't really translate the results of such a fit, of such a model of the background from the power spectrum directly to the light curve, to just remove the contribution from the star and then focus on the planet. So what we actually have to do is somehow find a way of doing this kind of description, but directly in the time domain. So doing this modeling in the time domain. And for this, I used Gaussian processes, which have been sort of used in the literature, but maybe not as systematically and in a way so connected to the way it is done in the power spectrum as I did. Now, Gaussian processes are stochastic processes. They basically model random phenomena, and they do this by having a mid-model of the data, and by also describing a covariance between the data. And the covariance is essentially described by a covariance function, or the kernel function. And the kernel function essentially just models the correlation between two different points in time. So the xn and xm would be t1 and t2. So two different points in time are correlated, and this kernel follows that correlation. It's also important to note that this kernel is actually dependent on a set of hyperparameters, which essentially controls some characteristics of this correlation, mainly, for example, characteristic timescales, characteristic amplitudes. Now, the interesting part about this kernel or this covariance function is if this covariance function between 2 points in time is actually only dependent on the distance in time between the two observations, it doesn't actually depend on the absolute time of them, then this kernel function is essentially an autocorrelation function. And the good thing about that is that we can directly, because they form a Fourier pair, we can directly translate from a power spectrum function into a autocorrelation function. And that's exactly what I do in my work. So I translate the the functions used for power spectrum fitting into an autocorrelation function or a kernel to use with Gaussian processes to model the stellar signals in the time domain. Now, unfortunately, not all is good with the Gaussian processes, and they are very computationally expensive. So it's not exactly trivial to just use them directly. What does exist are alternatives, alternative Gaussian process models. And what these do is they basically limit the functional form of the Gaussian processes that can be used in this modeling in exchange for reducing the computational time considerably. And that's exactly what I use. I use Celerity, which is an open source Python package that basically follows one of these trade-offs. And what I want to show next is basically the kernels that I have and how they compare to the actual signals used in background fitting in the power spectrum to see the differences and the similarities in the two models that I'm using, in the models that I'm using compared to the power spectrum. And so this is the case. So for the granulation for this function, RV-like function, we actually have in celerity we can model exactly the same function as we do in the power spectrum without any differences, which is great. Unfortunately, for the oscillations envelope, that's not the case. So I don't have access to a function like the Gaussian-like used for the oscillations envelope. What I do have is this similar function, which obviously clearly has differences. There's a plateau of power in the lower frequencies, and there's also higher power in the higher frequencies here. And this will obviously cause some changes in the way that in the characteristic parameters, so at time scales and amplitudes that I fit for my models, but it's approximate enough. And again, it centers on what would normally be defined as the Numax, and that is great. And so these are the models I use, again, together with a white noise model as well. These are the three components that I use to build my model of the stellar signals in the time domain. And so after doing this, basically, I define all these kernels to explain the stellar model. If I have a transit in my light curve that I want to model as well, I use it as the mean model of my GP. And then what I wanted to do was to try and do a comparison of this joint model with star and stellar part in the time domain against a bunch of stuff to see if it actually is behaving correctly, is recovering about the same values as it would normally be recovered for the power spectrum fitting. And so I compare this my time domain method against the power spectrum fitting for Kepler stars using diamonds. And it's important to note that in this first comparisons, I'm basically only using the stellar model. There's no transits there. So I'm only trying to compare exactly what the power spectrum fitting would do compared to the time domain. And I also do the same thing to compare against real values used to simulate TESS light curves. Although this TESS light curve was essentially simulated with the same description as the equations for the power spectrum fitting. And so obviously there's going to be differences. And finally, I compare the results against of extracting transits with my model with the stellar part, compared with a more naive model that doesn't consider any stellar signals in the light curve and only considers the transit. And so starting the results for the Kepler stars. So this is essentially trying to do background fitting for Kepler stars in the frequency domain with a battle-tested tool against my tool in the time domain and see how this compares. And what I find is that there's slight differences in the characteristics of some of the properties of the stellar signal. So for example, the characteristic timescales of the granulation are slightly different. The amplitudes are slightly lower, mostly because there's the contribution in the low power in from the oscillations envelope. But the good thing is that I actually basically recover the same Numax as the power spectrum fitting. Within 1%, I have all of these all of the Numax values recovered with a bias of 1%. The greatest deviation from the actual values is something like 3% at max between the value recovered by diamonds and the value I recover. And this is directly with in the time domain without ever looking at the power spectrum. So this is a representation of the power spectrum of those kernels, just to show a more usual view of the star, but my fit is then completely in the light curve. It doesn't include the power spectrum at all. And so going now to the TESS simulated light curves, the results are similar. So again, I have slight differences between the parameters that I recovered for the granulation, for example, and the true values used in the simulations, which makes sense because the simulations were essentially done with simulated with the functions normally used for background fitting in the frequency domain and then sampled for the time domain. Another thing that I note with TESS simulated light curves is that because the white noise is so large, I actually don't really constrain the second granulation, at least in both by what Diamonds was doing. I also tested Diamond with this data, and by what the time domain fitting is doing, and so it's just an interesting result for them to actually model the stellar signals in the time domain, that maybe the second granulation can't really be added to the model because it's just there's not enough data there to actually constrain it. And finally, even though the dispersion now is larger and I have some deviations of about 5%, the bias between my results, my new maxes recovered from the time domain fitting, and the actual new max values used for the simulation are within 0.5% of bias, which is actually really good. So I'm basically recovering the exact new max that is put into the simulations just by fitting stellar signals directly in the time domain. And so with kind of this tool now tested to actually recover stellar signals correctly, the interesting result would be to compare how this fares with the transits included there against just not considering the stellar part at all and just modeling exactly the same thing in the time domain just for the transits. And I do this by injecting transits into the TESS light curves from the previous study. So I've injected transits, so I know what the stellar properties should be, the stellar signal properties should be. I know what the transit signals should be. And essentially what I recovered is the stellar signals that I recover have about the same results that I had without having the transits there at all. And what I do find is that I do find for reduced bias in the recovery of the planetary radii. So the planetary radii that I recovered, obviously in relations to the star, are closer to the real, the truth, than without considering the stellar model at all. But the more interesting part also is that there's a lower dispersion in the values, in the offset between the actual value that I recover and the true values overall for all stars. So most stars seem to be more concentrated, very close to the actual real value. So not only is the sum of all of them, the bias, low, better, but there's also, most of them are very much closer to this actual true value, which is great. The other good result from this study is the fact that whenever my result is very far away from the truth, I seem to have larger uncertainties than the model that doesn't consider the stellar part, which is good because it reflects well the unknowns in that I have in the fitting. Meaning, when it's confident on the result, it seems to follow a good pattern. When it's not confident, it just increases the uncertainties, which gives us the confidence that we can trust that to be not confident in the result, and that is good. And so I just show here like a small example of what this transit fitting would be like with the stellar signals. And so you would see the transit model here in blue. You have the GP model in red, and notice that this GP model is essentially just a mean. So because this GP model is essentially modeling a random process, it doesn't actually output a specific function y of t. It actually outputs a distribution for each point in time t. And so we don't actually have a specific value for every point in time. We have a Gaussian distribution for every point in time, and you can actually sample this distribution to have a possible solution to what the stellar signals will look like in the time domain. Now, because we can actually constrain this model to the data that we have, but we can also just randomly sample it according to the time scales and amplitudes to just generate a random signal that would represent the stellar signals in the time domain. And so just to wrap up this characterization part, I've created a tool that models the stellar signals in the time domain together with the transits. It achieves very close results similar to the ones in the power spectrum fitting normally used for astroseismology for the background fitting. And it also recovers new max essentially with the same accuracy as the as power spectrum fitting, which is great. It seems that we're looking exactly at the same thing and finding the exact same things using this model in the time domain. And then using this tool together with the transits, I actually end up improving the accuracy of the recovered planetary parameters, which means that it is worthwhile to do all of this and modeling everything together instead of just trying to filter it out, which would not really happen for evolved hosts. Which means now I have a tool to actually do this characterization of giant planets around evolved hosts whenever I do have the new planets. And so the next part of the talk obviously is to actually look for those new planets. And to do that, to actually look for planets, there's a couple of steps that I needed to go through. So first I had to define a target list based on the TESS input catalog, a target list of interesting targets to look for planets around. The second part was to try and obtain systematics corrected light curves for all of the targets that I'm going to be in my target list that are actually observed by TESS. And then I want to search for the transits in them and validate these transits as actually physical transits, real transits, and whether they are planets or possible planets, or maybe eclipsing binaries or something else to discern them, and then to follow up on the interesting ones. And so the first thing is to try and actually define the target list that I was going to look at. And the first step in this target list, so all the data that I used for the target list selection was basically from the TESS input catalog directly. The first cut that I did was to try and get the giants out of the tick. And the idea was to do cuts in Gaia blue minus red colors, as well as absolute Gaia magnitude, which is calculated by using the parallaxes and using the apparent Gaia magnitudes from the tick. And these three cuts are essentially the three cuts that are highlighted here. Then there's also an extra cut that I did, which was with TESS magnitude lower than 10. The idea for this cut was mostly to try and target the bright stars in a way of, at the same time, reducing the sample size of this target list to try and make it feasible in time for me to do this work. And at the same time, to increase the probabilities of me having actual oscillations detected in these stars. Because again, I really want to have the oscillations on all of the hosts that I find to make sure that my characterization of the star is great, so that the characterization of the planet is also great. And so after doing this cut, the idea was to try and select all of the low luminosity red giant branch stars from this entire sample of giants. And the idea to do that was to do cuts in radius. And now, obviously, the TIC also provides a radius for these stars, normally computed by whatever is available for these stars. Now, the idea mostly with the cut in radius is to actually do a cut between 3 and 8 solar radii. And the idea is the 3 solar radii idea is to mostly make sure that if there are oscillations and they're detectable, they should be within the Nyquist limit for TESS long cadence data, so within 270 microhertz. And so that's the reason for the cut at 3 solar radii. And then the cut at 8 solar radii would be to make sure that the planets are actually detectable. And that the star is not too large for that. Now, because I wasn't completely confident in the uncertainties for the radius defined in the TIC, the idea was to try and stretch these limits out, and that's mostly the reason for the selection between 2.5 and 10 solar radii. And again, the sample from the out of the entire sample of giants you see is the red sample here in red. And this resulted in about, so this would be the sample of bright low luminosity RGB stars from the TIC. This results in about 100,000 stars for the all sky part. Now, because I started this work before TESS was finished with the northern hemisphere, I only started the work on the southern hemisphere. And so my sample of stars is actually of about 50,000 stars, of which about 40,000 are actually observed in cameras by TESS. And so that's the sample of stars that I actually have right now. It's a sample of 40,000 stars in the southern hemisphere of TESS. And so the next step was to try and have light curves for all of these stars, systematics corrected light curves. Now, targets observed by TESS in full frame images don't actually have light curves extracted by NASA. And so to find a way to actually have the light curves, I used Eleanor. Eleanor was a package developed essentially with the objective of extracting systematics corrected light curves for TESS FFI targets. which is kind of exactly what I want, although it was mostly focused on the main sequence stars and not exactly evolved stars. Now, one of the good things about Eleanor is that essentially it can target any star observed by TESS by simply providing the TESS input catalog ID. And with that, it knows the position of the TESS in the FFI, in the pixel files of the FFI. And so then what Eleanor does is that based on that position on the FFI, it extracts a target pixel file, so a collection of pixels around that target. The size of this square normally of pixels, it can be controlled by the user, but is usually in the order of about 15 by 15 pixels around the target. Then it does some background correction based on that target pixel file for the target, and then to actually extract the light curve, it does aperture photometry, but it makes sure to try a large collection of possible apertures, more common apertures. So what it does is for all of these possible apertures, it actually extracts the light curve with them. It does some systematics correction using the co-training basis vectors, which is a technique that is from some data provided by NASA. And then it actually computes a metric that evaluates the goodness of this final light curve for the extraction of transits. And so it does all of this extraction and correction for all of the apertures that it tries. And then based on this metric for extraction of transits, it chooses what would be the best aperture for this for this light curve. And this is just a small highlight of all of these steps from Eleanor. So this would be a target pixel file with about, again, 14, 15 pixels around the target. You'd have the 2D interpolated background of based on this target pixel file for this target, which is basically based on everything except what's inside the aperture chosen. In this case, you have this aperture chosen based on this list that you see on the right. Eleanor does have a flag where if you say that the field is too crowded, Eleanor only tries mostly the smaller apertures. It doesn't try the larger ones to make sure it doesn't catch any unwanted stars. And then based on this background and on this aperture, it extracts a light curve, and then it performs those corrections on this light curve to extract to give the final systematics corrected light curve for each of the test targets we're interested in. Now, unfortunately, this systematics correction doesn't work perfectly. There's a couple of issues there. And as I looked through all of my light curves extracted and corrected by Eleanor, I started to notice that specifically there were a lot of issues still left that seem to be very much similar for stars in the same sectors. And so I collected some examples just to show you of some things that I have. So this is for sector 8. There were sort of these issues at the beginning of the beginning of the orbits of TESS, which are present in the raw light curve as well. So up in the upper part, you have the raw light curve from Eleanor, and then the systematics corrected light curve from Eleanor. For sector 11, again, the same thing. And it's noticeable that Eleanor is doing some corrections. It just doesn't manage to do all of the correction, and is specifically missing at the start and the end of the orbits of TESS. And so this was a bit puzzling as to why this was happening. And so as I looked through the data releases from TESS for each of the TESS sectors, I noticed that there were basically considerable scattered light present at certain times during the observations. This is normally highlighted by NASA with a plot showing the scattered light during the orbits for TESS. Now, this scattered light should supposedly be somewhat accounted for in the corrections done by Eleanor, but for some reason it's missing at some specific points. And so I had to somehow solve this, because those types of noises, specifically very sharp decreases in flux, were mimicking transits a lot. And so my initial search was basically being very much guided by the noise and not exactly by actual transits of eclipsing binaries or planets. And so my idea, with lack of time to actually do a more complex and interesting solution, was to actually just look at a lot of samples of stars from each of the sectors, representative of each of the sectors, and try to have a collection of intervals of time to mask out of the light curve, so that this noise would be somehow just removed out of the light curve, and now whatever was left would be a good light curve, at least as best as possible. Now, obviously, this would reduce the duty cycle from my light curves, but the trade-off being that at least I'm looking at something that is should be actually signal and not just noise, which would be great for the search of planets. And that's exactly what I did. So here I'm showing again the same raw and corrected light curve from Eleanor. So in the left side, and on the right side, what you see is basically the same light curves, but now with my cuts applied on the top for the raw light curve and on the bottom for the corrected light curve. And so again, what is visible is that first, now the light curve seems a lot better. So there doesn't seem to be all of these issues at the beginning of the orbits, in this case for sector 8. And the other thing that is noticeable is that Eleanor is doing some corrections from the raw to the corrected, which means that, again, it's doing work, it's just not doing all of the work necessary. And again, I'll go through all the 3 examples from before. This is another one, and this is the last one, where we see that the corrected light curve with the cuts is actually looking a lot nicer than before. Now, unfortunately, it's not all good news, and there are some light curves where the issues still pop up. Now, because the amount of light curves with these issues now was a lot smaller than before, and mostly they weren't driving the results that I was getting from my search for planets, I didn't really bother to explore them further, so I don't really know totally what's causing the issues on these other problematic light curves. But for the most part, I have light curves that seem to be good for most of my 40,000 targets. And so the next step, now that the light curves are ready, was to actually define the search. Now, the search for transits around the light curves I do basically with 2 different methods. The first method is the box list squares, which is very commonly used in the literature. And it essentially just models the transit as a rectangular model, as you see here on the right. The transit list squares I also use is it's a more recent method that tries to improve on BLS with some trade-offs, but mostly tries to improve overall by adopting a more transit-like shape for the actual transits. Now, what both of these methods do exactly the same is that they, for a trial grid of possible periods for this planet, they essentially phase fold the light curve and try to fit this model they adopted to that phase folded light curve to see, and then they just output a metric based on how well this model fits the actual phase folded light curve. And so from all of these fits, it essentially considers the period with the highest metric as the one that is most probable to represent a good transit in this light curve. It might not be a real transit, it might just be noise, that there might not be anything there, but it outputs always based on this metric. And then what I do afterwards is that I actually, besides looking visually at these search results, I also do a automated false positive probability modeling of the transit fit to see if it actually, with Vespa, which is an automated tool to do this kind of false positive probability analysis, just to see if Vespa thinks this is a false positive or if it actually represents a planet as well. And so at the end of all of this search, without the actual validation, at the end of all of this search, I output a summary plot, where it is a plot where I essentially try to add all of the data that I have available for a single target after doing all of this work of creating the light curves and doing the search, which is something close to here. So you have the light curve on the top, the actual final light curve on the top with the corrections. You have the search results for both methods here on top and bottom. You have sort of a random frame that I take from the target pixel file, which obviously doesn't represent the neighborhood of the star for the entirety of the duration of the light curve, but at least it gives me an idea of the crowdedness of the field around this star, just to see if there might be some background stars that might be causing the signals that I'm seeing. There's some statistics about the search, and then there's also a periodogram from the light curve, so that I can try and see if there's oscillations or see if there's any weird stuff happening for this star. And this is mostly just to do the visual checkup of the transits. And so with this, I basically have an entirety of 40,000 stars with light curves, corrected light curves, and transit search for all of them. And I kind of wanted to go through some of the interesting results that I found from them, both in the context of astroseismology and also in the context of the planets. And so for astroseismology, the one thing that I note is that If I look at my light curves, specifically at the power spectrum of my light curves for stars with in the CVZ with 13 sectors of data, for the most part, I see oscillations there, and they're mostly very clear there. It even seems to be possible to recover individual frequencies from these light curves, which is great. Now, unfortunately, as I go to stars with two sectors of data here on the bottom left and with one sector of data on the bottom right, I do find some where I think there are oscillations present and they can be extracted. At the very least, a nu max should be extractable and maybe even a delta nu. But I should note that these, for two sectors of data and one sector of test data, these are very much the exception to the norm. And for the most part, these power spectrums are not that interesting in the context of astroseismology, which is not great because most of my stars obviously have one sector of test data. And so most of my planets should probably happen on those and not on the stars with the most data. Now, in the context of planets, I'm showing here in the initial results of my search, the 4 more interesting targets that I found and the conclusions that I've drawn from them. So the first 2 are actually great that I'm finding them because they're actually known evolved hosts. And so it's great that without actually constraining my model to try and look for them, it's great that my pipeline and my entire method is actually finding these again as very interesting candidates, which means that I'm finding the things that I know should be there. And then the last 2, I'm going to start by this one. So TIC348 is an actual candidate that I found, and I'm collaborating with some colleagues to try and actually get RV follow-up from this because it does seem to be an actual planet, and this would be a new one that would be fine. So it would be an extra one to add to the sample and to maybe improve those studies that I mentioned at the beginning. And the last one is interesting because it's, for the most part, it might be real, but if it's real, it's the first transit only. So this second transit, after looking at the neighborhood of this star and looking at the light curves extracted for stars neighboring this one, this transit, so this depth in the flux, this depression in the flux is actually caused by noise, and it's visible in 3 other stars at least, which means that obviously this result is actually a false result, and it's interesting to notice it because it just shows the importance of actually validating these candidates to make sure that what we're finding is actually real, or either an eclipsing binary or an actual planet, and not just noise left over from the light curve. And so that's why I mentioned that these 2 results of finding the exact things that we know are there are great to at least give us some trust in the actual quality of the light curves extracted. And so to conclude, during my PhD, I've basically then developed a tool that can model the stellar and the transit at the same time in the time domain. And I've shown that this tool not only recovers the stellar signals within the same precision as power spectrum fitting methods, the common ones normally used in astroseismology, but I also improved the recovered parameters for my transits, which is exactly what I want for this kind of evolved systems. So giant planets around evolved stars. I've also created the light curves for 40,000 bright low luminosity RGB stars in the southern hemisphere observed by TESS. These light curves, when enough data is there for the stars, meaning if I have 13 sectors, for the most part, these light curves seem to be ready to do astroseismology on them. Unfortunately, that doesn't really seem to be the case for most of the stars with one sector of data, but at least these stars with one sector of data seem to be at least good to look for planets, because I actually find some candidates there overall. I've also searched all of these light curves for the transit. So these candidates, I also have a list of these candidates which I'm now trying to validate. And so for the future, my idea, obviously, because I'm finishing the PhD, is to complete the classification of all of these planet candidates as real or not, and if they are planets or something else. And then hopefully, because actual confirmation of planet candidates takes a bit longer due to having to ask for RV follow-up and waiting for the results, or for positive RV follow-up. I'm thinking of doing determining the upper limit on the giant planet occurrence rate around the closing giant planets based on this southern sample from TESS. And obviously this is an upper limit because I would be using confirmed or validated planet candidates as my actual planets instead of confirmed actual planets. And then obviously afterwards I have to finish my PhD. But after this, there is the possibility of obviously first expanding this study for the Northern Hemisphere of the bright stars in the Northern Hemisphere by TESS, and then possibly just expanding it further for fainter magnitudes of TESS, because there's still plenty of stars. Obviously, it becomes even harder to detect the oscillations and even to detect the planets. But overall, it should be possible to just expand this further into more and more stars. And this is all for my project. Thanks.
Okay, so thank you very much, Filipe, for the great talk, and thank you for finishing right in time. So I don't see questions in the chat box. So if you do have questions, please raise your hand and we can go through. I do have a couple of questions. So one of them has to do with the library of 40,000 light curves that you have for red giants, right, in the Southern Hemisphere. Do you have plans to share those with the community? Because, you know, we can do seismology with those, right? Although perhaps with the one sector and two sector data, we will not have very high efficiency in terms of detecting oscillations, we can still have a go. Do you have plans to share those with us?
I mean, I'd be happy to share them. I don't really know how that works, except for just sending files to everyone. I imagine there's a way of like uploading them to Mast or just sharing them publicly somewhere. But yeah, I'd be okay with it.
Yeah, I'm sure we could find a structured way of
doing it. On TESSOC, yeah, Rasmus, on TESSOC, yes.
Yeah.
Because I mean, if for some reason I find a planet and someone has done astroseismology on them, that would be great, because that would give me already exactly what I want, which is the astroseismic the parameters from the stars using astroseismology, which is great. So yeah.
Okay, and my second question has to do with your list of candidates, right? So you showed us a few examples of promising potential planet candidates. So based on what you have found so far, what would you be able to infer right now regarding the occurrence rate of these planets around giant stars? Yeah. And how would that compare with the occurrence rate that has been previously found with K2?
I think the best comparison of the occurrence rate would mostly be also in concerned with the also with the simulations of the expected candidates that would be found for TESS. The studies of Sullivan 2015 and your study in 2018, and even with the occurrence rates, obviously there's still a need to account for the detectability of these systems with TESS due to the high noise. But it does seem that the number of actual candidates seems to be smaller than what would be expected. And so overall, it does seem to be that the occurrence rate seems to be either the occurrence rate is smaller, or just the noise on TESS is just too large. And so we're actually detecting a lot fewer of these candidates than what would be expected, at least the ones that seem to actually look like planet candidates, not just random candidates with transits.
I see that Dominic has a question. So Dominic, feel free to turn on your camera and pose your question, please.
Yep. Hi, Filipe. Thanks for the talk. I want to come back to the Eleanor extraction of light curves. Yeah. So I may have missed it, but could you comment on how many, as a fraction or number of stars, however you prefer, have this scattered light problem? I haven't run Eleanor with a large sample of stars. So
would you be asking before or after I do my cuts?
Before.
Oh, before. So I would say a very large number, mostly, and the reason mostly that I detected it like very, very clearly was that transit searches obviously try to, when they detect a transit, they have to try and detect the first instance of a transit in a light curve, meaning the epoch, the first time this transit happens. And what was happening mostly because these types of depths were being caused at the beginning of orbits, specifically for some sectors, what was happening is that most of my interesting planets based on the metrics from the search algorithms were basically all pointing to the same sectors with always very similar periods, meaning the periods of the orbits of TESS, about 11 to 13 days. And then the epochs seem to be all falling within the same 1 day period around the start of the first orbit on 2 or 3 sectors. And this was mostly obviously the examples I showed were the more clear ones, which were the ones that immediately popped up in this analysis of the interesting transits found by the search. And these are the ones that immediately put a red flag on me to actually look at them and see what was going wrong.
Yeah, I understand that. So the scattered light will always be a problem at the beginning or the end of an orbit. That's documented. But so you're saying that most of the extractions have this problem with Eleanor?
I can't really comment. I know some of the sectors don't really have that much of an issue. The number of them, the percentage of them in some of the sectors is not that large. But just to make sure that I wouldn't be controlled by these, by the few that were in some of the sectors, I still decided to cut about a day, I think, from the beginning of the orbits. Now, some of them were very clear, specifically the one where the scattered noise is less of a exponential drop and more of a random scatter. Those ones I had to cut. So I think it's sector 12. I had to cut about 3 days of data completely from the start of the light curve, because these ones were completely mimicking transits with their depth, and these seem to be present in most of them in that, or at least a lot of them in that sector.
Okay, so here's my question.
Yep.
When you do the cutting, do you do that in the time domain after you've ran Eleanor, or do you truncate the images that you feed to Eleanor and then reprocess them? Because that wasn't clear to me.
No, so the idea that I do right now is I actually cut it after Eleanor does the corrections. Yes. So because Eleanor is doing the correction based on the CBVs from NASA, and the CBVs have all of that supposedly from the beginning of the light curve, I let it run with all of that. And then I cut, obviously, because the analysis I did on the bad parts of the light curves were based on the corrected light curves from Eleanor. So my knowledge of where the cuts should be done are based on whatever was left from Eleanor and not exactly from the start.
Okay, that's great. No, that's all I need to know. Thank you.
And as Mikkel says there, I see, obviously the idea, as soon as the DAS light curves are available, is to run with them as well, just try and redo the search. And also I've tried to look at, for at least for some of the interesting targets, also look at the MIT quick look pipeline light curves, because obviously it's always great to try and look at a greater amount of light curves, because if the planets are present in all of them, it's a bit more trustworthy to know that the planet should be there. And so that's the idea, yes.
Okay, great. Thank you.
Thank you, Dominic. I see that Mikkel has a comment on this issue. Mikkel, perhaps you would like to turn on your camera and elaborate on that?
Sure. Well, I can only say that from the tests we have done so far, using our two different correction methods in the TADA pipeline, it seems to remove a lot of these issues just at the beginning of the orbits. But of course, as many will know, the data is not online yet. But we and in particular Rasmus is working very hard on having this done soon. But it's a lot of data to transfer. But hopefully it should help on some of these issues.
Yeah,
that's seen in Eleanor.
There's a thumbs up there by Dominic.
Yeah, I see that. So Margarita, you do have a question, right? So please turn on your camera.
No, I don't have a question. Sorry, that was a mistake.
Okay.
Sorry, Tiago.
No worries.
But well done, Philip. Yeah. I enjoyed your talk.
Hopefully, it wasn't too much planets for most people here, but I tried to veer it towards the stars part. But yeah.
Okay, good. So I don't see any more questions. So I would like to thank Filipe and thank you all for attending. We peaked at 80 participants today, so that was just short of the 90 participants from the first session, but we are doing very, very well, in my opinion. So we reconvene in 2 weeks. So the next session will still be announced, so stay tuned for that. And it will be for more of in a Pacific-friendly time schedule, right? But still try to attend if possible. So stay tuned for that, and thank you very much, and hope to see you in a couple of weeks.
Yes, thank you all for showing up as well for my talk, and thanks for the good vibes, people, for inviting me as well.